Stars in the galactic halo often appear isolated and unrelated, but precise measurements show that many of them are not moving independently. Groups of stars share the same velocity vectors, follow the same orbital paths, and display nearly identical chemical compositions. When these correlations are mapped across large areas of the sky, they reveal long, coherent structures extending tens to hundreds of thousands of light years. These structures are known as stellar streams. Stellar streams are elongated distributions of stars that originated in a single gravitationally bound system and were later pulled apart by tidal forces. They are among the clearest pieces of evidence that large galaxies grow by accreting and disrupting smaller ones. In the halo of a mature galaxy, streams function as physical records of past merger events, preserved not in photographs alone, but in the shared motion and chemistry of stars. A typical stellar stream forms when a dwarf galaxy or globular cluster enters the gravitational potential of a much larger host galaxy. The gravitational field experienced by the infalling system is not uniform. Stars on the side of the satellite closer to the host feel a stronger acceleration than those on the far side. This gradient in gravitational force produces tidal stretching. As the satellite continues along its orbit, repeated passages through regions of strong tidal stress gradually remove stars from the system. Once stripped, these stars remain on orbits similar to that of their parent system. They neither scatter randomly nor collapse back together. Instead, they spread out along the original orbital path, forming a leading arm of stars moving slightly ahead of the remnant and a trailing arm following behind. Over time, the separation between stars increases, but their velocities remain tightly correlated. This combination of spatial elongation and kinematic coherence defines a stellar stream. In dynamical terms, stellar streams are phase-mixed stellar populations. Phase space describes both the position and velocity of an object. Stars in a stream occupy a narrow region of velocity space while being extended across large distances in physical space. This property makes streams difficult to detect using imaging alone, especially when their surface brightness drops below roughly 30 magnitudes per square arcsecond. However, when full motion information is available, streams become sharply defined structures. Stellar streams are found almost exclusively in dynamically old galaxies. A dynamically old galaxy is one that has existed long enough for orbital evolution, tidal stripping, and phase mixing to operate over billions of years. In the early universe, galaxies were smaller, denser, and more chaotic. Their satellites had not yet experienced repeated orbits through a stable gravitational potential. As a result, long, thin streams could not form or persist. Galaxies like the Milky Way, with an age exceeding 13 billion years, have undergone extended periods of hierarchical growth. According to the cold, dark matter model of structure formation, large galaxies assemble through the gradual accretion of smaller systems. Most of these accretion events involve mass ratios of 10 to 1 or greater, meaning the smaller galaxy is eventually destroyed rather than merged intact. Stellar streams are the visible outcome of this process. The distinction between a bound satellite and unbound tidal debris is central to understanding streams. A bound satellite galaxy still possesses a gravitationally coherent core. Its stars orbit a common center, even if the system is distorted or losing mass. In contrast, unbound tidal debris has crossed an energetic threshold. The stars are no longer gravitationally bound to their original system. They now respond primarily to the gravitational potential of the host galaxy. This transition is gradual. During early stages of disruption, a satellite may retain a dense core while producing extended tidal tails. Over successive orbital periods, typically on timescales of several 100 million years per orbit, mass loss continues. Eventually, the remaining core dissolves entirely. At that point, the stellar stream persists without any surviving parent object. Once unbound, the stars in a stream cannot reassemble. Their internal velocity dispersion is too low to allow recollapse, and their orbits diverge over time due to slight energy differences. The stream slowly broadens and fades, but its kinematic coherence can remain detectable for several billion years, depending on the gravitational environment of the host galaxy. The idea that galaxies could be tidally disrupted developed gradually during the mid-20th century. In the 1950s, astronomers began applying classical tidal theory, long used to describe interactions between planets and moons, to much larger systems. The realization that galaxies are not rigid bodies but collections of stars orbiting in a shared potential led to new predictions about their behavior during close encounters. In 1962, Egan, Lindenbell and Sandage published a landmark paper proposing that the Milky Way formed through a rapid collapse. While later observations would revise this picture, their work emphasized the importance of stellar motions and phase space in reconstructing galactic history. Around the same time, other researchers explored how tidal forces could reshape galaxies during interactions. By the late 1960s and 1970s, numerical simulations of galaxy encounters became possible. These early simulations demonstrated that tidal interactions naturally produce extended stellar features, including tails and streams, even when the interacting galaxies differ greatly in mass. The simulations showed that repeated pericentric passages amplify tidal stripping, and that debris follows predictable orbital paths. Observational confirmation lagged behind theory for decades. Stellar streams are extremely faint and diffuse. Early photographic surveys lacked the sensitivity and sky coverage required to detect them reliably. Isolated detections of peculiar structures were often dismissed as background artifacts or statistical fluctuations. Progress accelerated with the advent of wide-field digital surveys and precise astrometric measurements. By measuring proper motions and radial velocities, astronomers could identify groups of stars moving together through the halo. The addition of spectroscopic data allowed chemical abundances to be measured with high precision. Chemical tagging provided an independent line of evidence. Stars formed in the same environment share similar abundance patterns in elements such as iron, magnesium, calcium, and heavier nuclei produced by supernovae. These chemical signatures persist for the lifetime of the stars. When widely separated stars exhibit both matching velocities and matching chemical fingerprints, their common origin becomes clear. Stellar streams therefore represent more than spatial structures. They encode information about the gravitational potential of the host galaxy, including the distribution of dark matter. The shape, width, and precession of a stream depends sensitively on the underlying mass distribution. Small perturbations along a stream can reveal interactions with dark matter subhalos, whose masses range from about 1 million to 100 million times that of the Sun. From an observational standpoint, stellar streams transform the galactic halo into a forensic archive. Each stream corresponds to a specific accretion event. Some formed recently and retain narrow, well-defined structures. Others are older, broader, and partially phase-mixed, approaching the smooth stellar halo. The Milky Way contains dozens of known stellar streams, and ongoing surveys continue to reveal more. Their existence confirms that the galaxy's growth has been continuous rather than monolithic. Accretion and disruption remain active processes even today. Stellar streams demonstrate that galactic evolution is governed by long-term gravitational dynamics rather than isolated formation events. They show how structure builds through repeated interactions and how the past remains observable long after the original systems have vanished. Before continuing deeper into specific examples and quantitative measurements, it is worth pausing briefly. If you enjoy exploring the structure and history of the universe through evidence like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow, and it supports the work behind these explorations. Stellar streams are not anomalies. They are expected outcomes of galaxy formation. Once identified and measured, they provide some of the most direct evidence available for how galaxies assemble, how gravity operates on vast scales, and how the remnants of long-destroyed systems continue to move together through space. The structure of the Milky Way reveals a long history of growth through accumulation rather than isolated formation. Its present-day shape, stellar populations, and kinematics all indicate that the galaxy is a merger remnant assembled over billions of years. This conclusion comes not from a single observation, but from multiple, independent lines of evidence that converge on the same picture. One of the clearest indicators lies in the Milky Way's stellar halo. Surrounding the bright disk and central bulge, the halo is a vast, diffuse population of stars extending far into intergalactic space. These stars follow elongated, often highly inclined orbits and display a wide range of chemical abundances. They differ fundamentally from the stars in the thin disk, which orbit in a relatively flat plane with nearly circular motions and more uniform metallicity patterns. The stellar halo contains only a small fraction of the galaxy's stars, yet it occupies an enormous volume. Estimates place the total stellar halo mass at roughly 1 to 2% of the Milky Way's total stellar mass. Given that the Milky Way contains on the order of 60 billion solar masses in stars, the halo accounts for approximately 600 million to 1.2 billion solar masses. This modest mass, spread across an immense region, produces an extremely low stellar density, making halo stars difficult to detect without precise measurements. The spatial extent of the halo is one of its most striking features. Observations show that halo stars are present well beyond 100,000 light-years from the galactic center. Some tracers, such as blue horizontal branch stars and RR Lyrae variables, have been identified at distances approaching 200,000 light-years. For comparison, the visible stellar disk of the Milky Way has a radius of roughly 50,000 to 60,000 light-years. The halo therefore extends at least twice as far as the disk and likely overlaps with the galaxy's dark matter halo, which reaches even farther. This structure does not arise naturally from star formation within a disk. Gas settles into rotating disks and forms stars efficiently in flattened configurations. The halo, by contrast, is dynamically hot. Its stars move on randomly oriented orbits, often with large vertical excursions above and below the galactic plane. Such motions point to an origin involving gravitational scattering, accretion, and violent relaxation, rather than in situ formation. Chemical evidence reinforces this conclusion. Many halo stars are metal-poor, meaning they contain lower abundances of elements heavier than helium compared to disk stars. These chemical signatures indicate formation early in cosmic history, before successive generations of stars enriched the interstellar medium with heavy elements. At the same time, the halo displays a wide spread in metallicity, inconsistent with a single, well-mixed, star-forming environment. This diversity suggests that halo stars originated in multiple small systems, each with its own star formation history. The Milky Way also contains distinct stellar populations whose properties cannot be explained by internal evolution alone. The thick disk, for example, consists of stars with larger vertical scale heights and higher velocity dispersions than the thin disk. Its stars are typically older and more metal-poor. Numerical simulations show that minor mergers can heat a pre-existing thin disk, puffing it up into a thick disk. The presence of this component therefore supports a history of accretion events rather than uninterrupted disk growth. Taken together, these features indicate that the Milky Way did not form as a single, monolithic object. Instead, it grew through a sequence of mergers, absorbing smaller galaxies over cosmic time. This process is a central prediction of hierarchical structure formation, the framework underlying the standard lambda-CDM cosmological model. In lambda-CDM cosmology, structure forms from the bottom up. Small fluctuations in the density of dark matter in the early universe collapse first, forming low-mass halos. Over time, these halos merge and accrete matter, building progressively larger systems. Baryonic matter follows this dark matter, scaffolding, cooling, and forming stars within the gravitational wells provided by the halos. Under this model, galaxies like the Milky Way are assembled through numerous merger events, most of which involve much smaller companions. Major mergers between galaxies of comparable mass are relatively rare for disk galaxies, as such events tend to disrupt disks entirely. Minor mergers, with mass ratios of 10 to 1 or greater, are far more common and leave subtler but cumulative signatures. These include stellar streams, a diffuse halo, and kinematic heating of the disk. The stellar halo represents the integrated debris from these minor mergers. Each accreted dwarf galaxy contributes stars to the halo as tidal forces strip them from their original system. Over time, the debris from many such events overlaps and phase mixes, producing the smooth background halo observed today, punctuated by coherent substructures such as streams and shells. Numerical simulations of galaxy formation within the Lambda CDM framework reproduce these features with remarkable consistency. Simulated Milky Way-like galaxies develop extended stellar halos with masses and density profiles similar to those observed. They also show a combination of smooth components and identifiable substructures, reflecting both ancient and more recent accretion events. The idea that the Milky Way's structure encodes its formation history has roots that extend back more than half a century. One of the earliest systematic attempts to reconstruct the galaxy's past came from the work of Egan, Lynden-Bell and Sandage in 1962. Their influential study analysed the motions and metallicities of nearby stars and proposed that the Milky Way formed through a rapid, coherent collapse of a proto-galactic cloud. In their model, the galaxy began as a roughly spherical distribution of gas that collapsed on a timescale of a few 100 million years. As the collapse progressed, stars formed with decreasing orbital eccentricities and increasing metallicities. This scenario explained certain correlations observed in the local stellar population and emphasized the importance of phase space information in understanding galactic evolution. While later observations would challenge the idea of a single rapid collapse, the work of Egan, Lynden-Bell and Sandage established several enduring principles. It highlighted the value of stellar kinematics and chemical abundances as fossil records of formation processes. It also framed the Milky Way as a system whose present structure reflects its past dynamics. Subsequent studies, particularly from the 1980s onward, revealed inconsistencies with a purely monolithic collapse. The discovery of satellite galaxies, the identification of stellar streams, and the recognition of multiple distinct halo components all pointed toward a more complex assembly history. Rather than collapsing in isolation, the Milky Way grew through continuous accretion. Modern data have refined this picture further. Precise measurements of stellar motions show that the halo is not a single, uniform population. Instead, it contains stars on a wide range of orbits, including highly radial trajectories indicative of past merger events. Chemical abundance studies demonstrate that many halo stars share signatures consistent with formation in small, chemically unevolved systems rather than in the main body of the galaxy. The mass distribution of the halo also carries information about the merger history. A halo mass of 1 to 2% of the total stellar mass implies that the Milky Way has accreted the equivalent of several dwarf galaxies over its lifetime. Some of these mergers were significant enough to leave lasting imprints on the galaxy's structure, while others contributed only diffuse debris now blended into the background halo. The extended size of the halo reflects the long dynamical timescales involved. At distances beyond 100,000 light-years, orbital periods can reach several billion years. Debris deposited in these regions remains coherent for long durations, preserving evidence of ancient accretion events. This persistence allows astronomers to probe the Milky Way's early growth, reaching back to epochs when the universe itself was only a few billion years old. The Milky Way therefore functions as a cumulative record of hierarchical assembly. Its halo stars, their motions, and their chemical compositions collectively demonstrate that the galaxy has grown by consuming smaller systems. This process remains ongoing. Several satellite galaxies continue to orbit the Milky Way today, and tidal interactions are actively reshaping them. Understanding the Milky Way as a merger remnant provides a unifying framework for interpreting its structure. The halo is no longer seen as a minor, peripheral component, but as a key archive of the galaxy's past. Its low mass fraction belies its scientific importance, as it contains information inaccessible through studies of the disk alone. As attention turns from general evidence to specific events and identifiable debris, the abstract picture of hierarchical growth becomes concrete. Individual mergers can be reconstructed, their timelines estimated, and their contributions measured. Stellar streams play a central role in this effort, serving as direct tracers of accretion in action and in memory. This perspective sets the stage for examining particular cases where the Milky Way's cannibalistic nature is visible in detail. Some systems are still in the process of being dismantled, offering direct insight into how stars are redistributed into the halo. Others have already dissolved, leaving behind only faint, extended trails that record the paths they once followed. Tidal forces arise naturally in any extended gravitational system. In a galactic context, they govern how smaller stellar systems respond when they orbit within the gravitational potential of a much larger galaxy. These forces explain in quantitative terms how dwarf galaxies and globular clusters are transformed into elongated stellar streams. The key concept is that gravity from a massive galaxy does not act uniformly across an orbiting satellite. The side of the satellite closer to the galactic center experiences a stronger gravitational acceleration than the far side. This gradient in force is small on stellar scales, but significant across objects that span hundreds or thousands of light years. Over time, this differential acceleration alters stellar orbits inside the satellite and can unbind stars from it. A useful way to describe the boundary between gravitational stability and disruption is the Roche limit. In its original formulation, the Roche limit defines the distance at which a self-gravitating body orbiting a more massive object can no longer hold itself together against tidal forces, while the classical Roche limit was developed for fluid bodies such as moons orbiting planets. The same principle applies to stellar systems orbiting galaxies with important modifications. In a galactic potential, the Roche limit is not a single sharp radius. Instead, it depends on the mass distribution of both the satellite and the host galaxy, as well as on the satellite's orbital parameters. The relevant quantity is the tidal radius, sometimes called the Jacobi radius. This radius defines the region within which stars remain gravitationally bound to the satellite, despite the host galaxy's tidal field. The tidal radius decreases as the satellite moves closer to the galactic center. During each pericentric passage, when the satellite reaches the closest point in its orbit, the tidal forces peak. Stars that lie near or beyond the tidal radius at that moment can gain enough energy to escape the satellite's gravitational influence. This process repeats with every orbit, leading to progressive mass loss. The physics of this stripping process is governed by differential gravity. Stars inside the satellite occupy slightly different positions relative to the galactic center. Those on the near side feel a stronger pull toward the host galaxy and tend to drift ahead of the satellite along the orbit. Stars on the far side feel a weaker pull and lag behind. This asymmetry naturally produces two tidal arms, a leading arm and a trailing arm. The stars that escape do not receive random impulses. Their velocities differ only slightly from that of the satellite's center of mass. As a result, their orbits remain similar to the original orbit of the satellite, differing mainly in orbital phase rather than shape. This is why stellar streams trace the orbital paths of their progenitors so closely. The stretching of a satellite into a stream can be understood in terms of energy and angular momentum dispersion. When a star becomes unbound, it carries with it a small offset in orbital energy and angular momentum relative to the satellite's mean values. Stars in the leading arm typically have slightly higher orbital energy and slightly lower angular momentum, allowing them to move ahead along the orbit. Stars in the trailing arm have slightly lower energy and higher angular momentum, causing them to fall behind. These differences are small, but over time they accumulate. As stars continue orbiting the galaxy, their slight energy offsets translate into steadily increasing separations along the orbit. The stream lengthens while remaining narrow in velocity space. This gradual separation explains why streams can extend for tens or hundreds of thousands of light years without dispersing completely. Angular momentum plays a central role in maintaining the coherence of streams. Because the stripped stars originate from a common orbit, their angular momentum vectors are closely aligned. This alignment keeps the stream confined to a narrow orbital plane, at least initially. Deviations from this plane arise slowly due to perturbations from the galactic potential, interactions with other satellites, and encounters with dark matter substructure. The alignment of streams with orbital paths is therefore a direct consequence of conservation laws. Energy and angular momentum are approximately conserved during stripping, with only small perturbations introduced by tidal forces. The resulting debris follows trajectories that map the underlying gravitational potential of the host galaxy with high fidelity. This property makes stellar streams valuable dynamical tracers. By modelling the shape, precession, and thickness of a stream, astronomers can infer details about the galaxy's mass distribution, including the shape and extent of its dark matter halo. Streams effectively act as test particles released at known times and energies, providing a natural experiment in galactic dynamics. The rate at which a satellite loses mass depends on several factors. The most important are the satellite's internal density, its total mass, and the eccentricity of its orbit. Compact systems with high central densities, such as dense globular clusters, resist tidal stripping more effectively than diffuse dwarf galaxies. Satellites on highly eccentric orbits experience stronger tidal forces at pericenter and therefore disrupt more rapidly. Orbital timescales set the rhythm of disruption. In the inner halo of a galaxy, orbital periods are typically on the order of a few 100 million years. In the outer halo, periods can extend to several billion years. Each pericentric passage acts as a stripping event, removing additional stars from the satellite. Over many orbits, these losses accumulate. For a typical dwarf galaxy orbiting within the Milky Way's halo, significant tidal stripping can occur over 1 to 3 billion years. Complete disruption may take longer, depending on the satellite's initial mass and structure. Some systems survive for many orbits, gradually shedding stars until only a dense remnant remains. Others dissolve more quickly, leaving behind a stream without a surviving core. Globular clusters follow a similar process, but on different scales. Their higher internal densities give them smaller tidal radii and greater resistance to disruption. When they do form streams, those streams are usually thinner, often only tens to a few hundred light years wide. Despite their smaller size, these streams can remain coherent for billions of years, particularly in regions of the halo with weak tidal perturbations. The long timescales involved explain why stellar streams serve as records of ancient events. A stream formed several billion years ago can still be identifiable today, especially if it orbits at large galactocentric distances where dynamical mixing proceeds slowly. In contrast, streams in the inner galaxy phase mix more rapidly due to stronger tidal fields and more frequent perturbations. Phase mixing gradually erases the contrast between the stream and the surrounding halo. Small differences in orbital period cause stars to spread around the orbit, eventually filling it more uniformly. This process does not destroy the stream immediately, but it reduces its surface density and makes detection more challenging. The timescale for complete phase mixing can range from a few billion years in the inner halo to well over 10 billion years in the outer regions. The interplay between stripping and phase mixing determines how long a stream remains observable. Recently formed streams appear narrow, high contrast, and well-defined. Older streams are broader, more diffuse, and sometimes only detectable through kinematic or chemical signatures. Both types contain valuable information about the galaxy's past. Tidal disruption also transfers energy and angular momentum between the satellite and the host galaxy. Although the effect on the host is small for minor mergers, repeated accretion events contribute cumulatively to the evolution of the galaxy's halo and disk. Over cosmic time, these interactions help shape the overall structure of the galaxy. The physics described here operates continuously in massive galaxies. Satellites are captured, orbits decay through dynamical friction, and tidal forces reshape stellar systems. The resulting streams are not anomalies, but expected outcomes of long-term gravitational evolution in a hierarchical universe. Understanding tidal forces and the mechanics of disruption provides the foundation for interpreting observed stellar streams. It explains their shapes, orientations, and longevity. It also clarifies why streams align with orbital paths and why their internal motions remain so coherent over immense distances. With this physical framework in place, individual streams can be analysed as specific realizations of the same underlying process. Each stream encodes details about its progenitor, its orbit, and the galactic potential it moves through. By decoding those details, astronomers reconstruct the sequence of events that built the Milky Way's halo star by star, orbit by orbit. The Sagittarius dwarf spheroidal galaxy provides one of the clearest, best documented examples of a galaxy undergoing tidal destruction in real time. Its discovery, structure, orbit, and extensive stellar debris offer a direct observational demonstration of how large galaxies grow by dismantling smaller ones. Among all known stellar streams in the Milky Way halo, the Sagittarius system stands out for its scale, clarity, and scientific importance. The galaxy was identified in 1994 by Rodrigo Ibarta, working with collaborators Michael Irwin and Jerry Gilmore. The discovery emerged from a kinematic survey of stars towards the galactic center, a region heavily obscured by dust and crowding. While analyzing stellar velocities, Ibarta noticed a population of stars moving coherently but distinctly from the surrounding Milky Way stars. These stars shared a common radial velocity pattern, inconsistent with any known galactic component. Follow-up observations revealed that this population formed a gravitationally bound system, a dwarf spheroidal galaxy located behind the central bulge of the Milky Way. This object became known as the Sagittarius dwarf spheroidal galaxy, often abbreviated as Sagittarius DSPH. Its position on the sky, near the constellation Sagittarius and close to the galactic plane, had concealed it from earlier surveys. At the time of discovery, Sagittarius was already in an advanced state of tidal disruption. Its stellar distribution appeared elongated and its velocity dispersion showed signs of significant tidal heating. Subsequent studies quickly established that the galaxy was not an isolated satellite, but one actively being torn apart by the Milky Way's gravitational field. The present-day remnant of the Sagittarius dwarf lies at a distance of approximately 70,000 light-years from the galactic center, equivalent to about 21 kiloparsecs. This places it well within the Milky Way's stellar halo and on an orbit that repeatedly brings it through regions of strong tidal stress. Its current position is near pericenter, where tidal forces are strongest and mass loss is most efficient. Orbital modelling indicates that Sagittarius follows a nearly polar orbit, inclined steeply relative to the Milky Way's disk. Its orbital period is estimated to lie between 0.85 and 1 billion years. Each orbit carries the galaxy from the outer halo deep into the inner regions of the Milky Way, subjecting it to repeated tidal shocks. These repeated passages have progressively stripped stars and dark matter from the system. The most striking feature associated with Sagittarius is its stellar stream. As stars were removed from the dwarf galaxy during successive orbits, they spread out along its orbital path. Over time, this debris formed an enormous, coherent structure wrapping around the Milky Way multiple times. Observations show that the Sagittarius stream spans the entire sky and extends over several full orbital wraps. In total length, the stream exceeds 360 degrees in angular extent and traces a path that loops around the galaxy at least 2 and likely 3 times. In physical terms, this corresponds to a structure hundreds of thousands of light-years long. No other known stellar stream in the Milky Way approaches this scale. The stream is composed of both a leading arm and a trailing arm. The leading arm moves ahead of the surviving core of the dwarf galaxy along its orbit, while the trailing arm follows behind. These arms occupy different regions of the sky and probe different distances from the galactic centre, allowing astronomers to sample the Milky Way's gravitational potential over a wide range of radii. Distance measurements along the stream reveal substantial variation. Portions of the stream approach within about 50,000 light-years of the galactic centre, while other segments extend beyond 100,000 light-years. This broad radial coverage makes the Sagittarius stream an exceptionally powerful probe of the Milky Way's mass distribution, particularly the shape and extent of its dark matter halo. Estimating the original mass of the Sagittarius dwarf galaxy requires reconstructing how much material has already been lost. Present-day measurements of the remaining core suggest a stellar mass of only a few times 10 to the 7th solar masses. However, the total stellar mass contained in the stream is much larger. Combined estimates indicate that Sagittarius has lost the majority of its original stellar content. Reconstructions based on star counts and stellar population modelling suggest that the progenitor galaxy likely had an initial stellar mass of several times 10 to the 8th solar masses. This places it among the more massive dwarf galaxies accreted by the Milky Way. Over the course of multiple orbits, tidal stripping removed a large fraction of these stars, redistributing them into the halo. Dark matter stripping has been even more severe. Dwarf spheroidal galaxies are strongly dominated by dark matter, particularly in their outer regions. Tidal forces preferentially remove this extended dark matter halo early in the disruption process. Simulations indicate that Sagittarius likely lost most of its dark matter during its first few pericentric passages, leaving the stellar component increasingly vulnerable to further stripping. This sequence of events follows theoretical expectations. As dark matter is stripped away, the gravitational binding of the remaining stars weakens. Subsequent tidal interactions then remove stars more efficiently, accelerating the galaxy's dissolution. The present-day remnant of Sagittarius is therefore only a small fraction of its former self, held together by a much-reduced gravitational potential. The internal stellar populations of Sagittarius provide additional insight into its history. The galaxy contains multiple stellar populations spanning a range of ages and metallicities. Some stars are more than 10 billion years old, while others formed as recently as a few billion years ago. This extended star formation history indicates that Sagittarius was once a relatively massive system capable of retaining gas and forming stars over long periods. Chemical abundance measurements show that Sagittarius stars are, on average, more metal-rich than stars in many other dwarf spheroidal galaxies. This enrichment reflects sustained star formation and chemical evolution prior to accretion. Along the stream, metallicity gradients are observed, with more metal-rich stars concentrated closer to the remnant core and more metal-poor stars dominating the outer debris. This pattern matches predictions from tidal stripping models, in which outer, less tightly bound populations are removed first. The Sagittarius system has also influenced the Milky Way itself. Numerical simulations indicate that its repeated passages through the galactic disk may have contributed to vertical oscillations and warping of the disk. Some models suggest that interactions with Sagittarius played a role in exciting spiral structure or inducing ripples observed in the disk's stellar density. From a dynamical perspective, Sagittarius serves as a test case for understanding satellite disruption in realistic galactic potentials. Its extensive stream has been used to constrain the shape of the Milky Way's dark matter halo, with particular focus on whether the halo is spherical, oblate, or triaxial. While early models favoured a spherical halo, later analyses incorporating the full extent of the stream suggest more complex geometries. The system also highlights the limitations of simplified models. The orbit of Sagittarius has evolved over time due to dynamical friction, mass loss, and changes in the Milky Way's potential. As the dwarf lost mass, its orbit likely expanded slightly, altering the spacing and orientation of successive stream wraps. Accurate modelling therefore requires self-consistent simulations that account for both the satellite's evolution and the host galaxy's response. Sagittarius is often described as a galaxy in the act of dying, but this description has a precise physical meaning. The system is undergoing irreversible tidal dissolution. Each orbit removes additional material, and the remaining core continues to lose mass. Eventually, the remnant will dissolve completely, leaving only a diffuse overdensity embedded within its own stream. The timescale for this final dissolution is uncertain, but likely lies within the next few billion years. By that time, the coherent core will vanish, and Sagittarius will exist only as stellar debris spread throughout the halo. Its stars will continue to orbit the Milky Way, but their common origin will become increasingly difficult to detect as phase mixing progresses. Despite this eventual fate, Sagittarius currently provides an unparalleled opportunity to study galactic cannibalism in detail. It allows astronomers to connect theoretical models of tidal disruption with direct observations of stars, velocities, and chemical abundances. Few other systems offer such a complete view of the process from bound satellite to extended stream. Sagittarius demonstrates that the Milky Way's growth is not an abstract concept inferred only from simulations or distant galaxies. It is an ongoing process, observable within our own galaxy. The stars torn from Sagittarius now populate large regions of the halo, contributing directly to its mass, structure, and chemical diversity. In this sense, the Sagittarius dwarf spheroidal galaxy represents a critical link between theory and observation. It confirms that stellar streams are the expected outcome of hierarchical galaxy formation. It shows how dark matter and stars respond differently to tidal forces. And it provides a concrete example of how a once-independent galaxy becomes part of a larger system, star by star, orbit by orbit. As attention shifts from this prominent example to subtler, thinner streams, the physical principles remain the same. Sagittarius simply reveals them on the largest and most accessible scale, making it a cornerstone in the study of stellar streams and galactic evolution. Stellar streams do not all share the same physical origin. Their appearance, internal structure, and kinematic properties depend strongly on the nature of the system that produced them. One of the most informative distinctions is between streams formed by globular clusters and those formed by dwarf galaxies. Although both are created by tidal disruption, the differences in their mass, internal structure, and stellar populations leave clear, measurable signatures in the resulting streams. Globular clusters are compact, gravitationally bound systems typically containing between 10,000 and several million stars. Their total masses usually range from about 10 to the power of 4 to 10 to the power of 6 solar masses, and their half-light radii are only a few tens of light years. Dwarf galaxies, by contrast, are far more extended and massive. Even the smallest classical dwarf spheroidal galaxies have stellar masses of 10 to the 7th to 10 to the 9th solar masses and sizes measured in thousands of light years. Crucially, dwarf galaxies are embedded in massive dark matter halos, while globular clusters are not. These fundamental differences determine how each system responds to the Milky Way's tidal field and how their debris appears once stripped. Streams originating from globular clusters are among the thinnest and dynamically coldest stellar structures known in the galaxy. Typical widths range from roughly 30 to 300 light-years. In angular terms, many of these streams subtend only a fraction of a degree on the sky, even when they extend for tens of thousands of light-years in length. Their narrowness reflects the compact size and low internal velocity dispersion of their progenitors. The velocity dispersion within a globular cluster is usually on the order of 1 kilometer per second, equivalent to about 0.6 miles per second. When stars escape the cluster, they do so with only very small differences in energy and angular momentum relative to the cluster's orbit. As a result, the stripped stars remain tightly confined in phase space. The stream grows longer with time, but its cross-sectional thickness remains small. Dwarf galaxy streams present a stark contrast. Their widths commonly reach several thousand light-years, sometimes exceeding 10,000 light-years in extreme cases. This increased thickness arises from both the larger physical size of the progenitor and its higher internal velocity dispersion. Dwarf galaxies typically exhibit stellar velocity dispersions of 5 to 15 kilometers per second, or about 3 to 9 miles per second, even before disruption begins. When stars are stripped from a dwarf galaxy, they carry a wider range of energies and angular momenta. Over time, this dispersion translates into broader streams that occupy a larger volume of the galactic halo. These streams often appear more diffuse and are harder to detect photometrically, even though they may contain far more stars than globular cluster streams. Velocity dispersion provides one of the most powerful diagnostics for distinguishing between the two types of streams. In globular cluster streams, the dispersion of stellar velocities perpendicular to the stream is extremely small, often below 1 kilometer per second. Along the stream, velocity gradients are smooth and tightly correlated with position, reflecting the gradual separation of stars along the orbit. In dwarf galaxy streams, velocity dispersions are significantly larger. Stars at the same location along the stream can exhibit a range of velocities several kilometers per second wide. This internal kinematic spread reflects the more complex gravitational history of dwarf galaxies, including the influence of dark matter and prolonged tidal heating prior to complete disruption. Chemical composition offers an equally important distinction. Globular clusters are among the most chemically homogeneous stellar systems known. With rare exceptions, stars within a single globular cluster formed in a short burst from well-mixed gas. As a result, they share nearly identical ion abundances and exhibit only limited variations in light elements. When a globular cluster forms a stream, this chemical uniformity is preserved. Stars along the stream display almost identical metallicities, typically varying by less than 0.05 decs in ion abundance. This homogeneity allows astronomers to chemically tag stream members with high confidence, even when spatial or kinematic data are incomplete. Dwarf galaxies, in contrast, experience extended star formation histories. Their lower gravitational potentials allow gas to be lost and reaccreted over time, and successive generations of stars form with progressively higher metallicities. As a result, dwarf galaxies show broad metallicity distributions, often spanning more than 1 decs in ion abundance. Streams formed from dwarf galaxies retain this chemical diversity. Along a single stream, stars can exhibit a wide range of metallicities, reflecting their origin in different regions of the progenitor. In many cases, metallicity gradients are observed along the stream, with more metal-rich stars concentrated near the surviving core and more metal-poor stars dominating the outer debris. This pattern arises because the outer regions of dwarf galaxies are stripped first. These differences make chemical abundance measurements a critical tool for identifying the nature of a stream's progenitor. A narrow metallicity distribution strongly favours a globular cluster origin. A broad distribution, especially when combined with multiple stellar populations, points toward a dwarf galaxy. Two well-studied examples illustrate this contrast clearly: the stream associated with Palomar 5 and the stream produced by the Sagittarius dwarf galaxy. Palomar 5 is a low-mass globular cluster currently located about 75,000 light-years from the galactic center. Despite its modest mass, it exhibits spectacular tidal tails extending more than 20 degrees across the sky, corresponding to a physical length of over 30,000 light-years. The stream is remarkably thin, with a width of roughly 100 light-years, and displays an exceptionally low internal velocity dispersion. Stars along the Palomar 5 stream share nearly identical metallicities, centered around an iron abundance of approximately 1/10 that of the Sun. This chemical uniformity confirms their origin in a single, short-lived star formation event. The stream also shows small gaps and density variations, which have been used to study perturbations from dark matter subhalos and the Milky Way's disk. In contrast, the Sagittarius stream represents the disruption of an entire dwarf galaxy. Its width varies along its length, but commonly reaches several thousand light-years. The stream wraps around the Milky Way multiple times and contains stars spanning a wide range of metallicities, from relatively metal-rich populations to stars with abundances well below 1/10 solar. Velocity measurements along the Sagittarius stream reveal dispersions of several kilometers per second, far larger than those seen in globular cluster streams. These properties reflect both the original structure of the Sagittarius dwarf and the complex sequence of tidal stripping events it has experienced over billions of years. The presence or absence of dark matter is another decisive factor. Globular clusters are not embedded in dark matter halos, or if they are, the halos are negligible compared to their stellar mass. Their tidal evolution is therefore governed almost entirely by their stellar self-gravity. Once stars escape, the cluster's mass decreases rapidly and disruption can proceed quickly. Dwarf galaxies, by contrast, begin their interaction with the Milky Way dominated by dark matter. Early tidal stripping preferentially removes dark matter from the outer halo, leaving the stellar component initially less affected. As dark matter is lost, the stellar body becomes more vulnerable, and tidal stripping accelerates. This two-stage process produces streams that record both the dark matter-dominated and star-dominated phases of disruption. These physical differences also influence how long streams remain detectable. Thin globular cluster streams can remain coherent for billions of years, especially if they orbit at large galactocentric distances where tidal perturbations are weak. Their narrow widths and low velocity dispersions allow them to persist as high-contrast structures against the background halo. Thick dwarf galaxy streams may remain identifiable over similar or even longer timescales due to their large stellar content, but their lower surface brightness and greater dispersion make them more challenging to detect. Over time, they blend more smoothly into the stellar halo, contributing to its diffuse background, rather than standing out as distinct filaments. From an observational perspective, distinguishing between thin and thick streams is essential for reconstructing the Milky Way's accretion history. Thin streams trace the disruption of globular clusters and provide precise probes of the galactic gravitational potential on small scales. Thick streams trace the accretion of dwarf galaxies and reveal the galaxy's growth in mass and complexity over cosmic time. Together, these two classes of streams demonstrate that the Milky Way's halo is built from multiple types of building blocks. Some contributions come from compact, chemically simple systems. Others originate in extended, chemically complex galaxies. Each leaves a distinct imprint in the structure, kinematics, and chemistry of the halo. Understanding these differences allows astronomers to classify newly discovered streams, estimate the properties of their progenitors, and place each structure within the broader narrative of galactic assembly. Thin and thick streams are not merely variations on a theme. They represent fundamentally different pathways through which stars are transferred from independent systems into the halo of a larger galaxy. With these distinctions established, attention can turn to how modern surveys detect and characterize streams with increasing precision. Advances in astrometry and spectroscopy have transformed the identification of both thin and thick streams, revealing a far richer and more complex halo than was previously imagined. The study of stellar streams entered a new phase with the launch of Gaia. Before Gaia, the existence of streams was inferred from limited sky surveys, radial velocity measurements, and deep photometric imaging. These methods revealed a handful of prominent structures, but they offered only partial information. Positions were often uncertain, motions were incomplete, and distances were poorly constrained. Gaia changed this by measuring the Milky Way in motion, star by star, across nearly the entire sky. Gaia was launched by the European Space Agency on December 19, 2013, and placed into a stable orbit around the Sun-Earth L2 Lagrange point. From this position, about 1.5 million kilometers from Earth, the spacecraft could scan the sky continuously with exceptional stability. Its primary objective was ambitious: to create a three-dimensional map of the Milky Way and measure the motions of its stars with unprecedented precision. The core innovation of Gaia lies in astrometry, the precise measurement of stellar positions and motions. Gaia repeatedly observes each star as the spacecraft slowly rotates, allowing it to track changes in position over time. From these repeated measurements, Gaia determines a star's parallax, which gives distance, and its proper motion, which gives motion across the sky. When combined with radial velocity measurements from onboard spectroscopy for brighter stars, this yields full three-dimensional velocities. The precision of Gaia's measurements represented a step change in capability. For bright stars, proper motion uncertainties reached the level of tens of micro-arc seconds per year. To put this in physical terms, a micro-arc second corresponds to the apparent size of a coin on the Moon as seen from Earth. At a distance of 10,000 light-years, a proper motion precision of 10 micro-arc seconds per year translates into velocity uncertainties of only a few hundred meters per second. This level of accuracy is well matched to the internal motions of stellar streams. The first major public release of Gaia data, known as Data Release 2, or Doctor 2, occurred in April 2018. This release included precise positions, parallaxes, and proper motions for more than 1.3 billion stars, along with radial velocities for about 7 million of them. For the first time, astronomers had access to coherent motion information across the Milky Way on a truly global scale. The impact on stellar stream research was immediate. Within months of Doctor 2, multiple groups reported the discovery of new stellar streams using purely kinematic criteria. Instead of searching for faint overdensities on the sky, researchers could now search for stars sharing the same motion through space. Stars that appeared unrelated in images suddenly revealed themselves as members of coherent dynamical structures. This shift marked a fundamental methodological change. Stellar streams could now be identified in velocity space rather than spatial space. Even streams with extremely low surface brightness, invisible in photometric surveys, became detectable through their shared kinematics. This greatly expanded the known population of streams in the Milky Way halo. The number of known streams increased rapidly. Before Gaia, fewer than a dozen well-defined streams were recognized in the Milky Way. After Doctor 2, that number grew to several dozen. Many of these newly identified streams were thin, dynamically cold structures consistent with globular cluster progenitors. Others were broader and more complex, indicative of disrupted dwarf galaxies. Gaia's third major data release, Doctor 3, published between 2022 and 2023, further refined this picture. Doctor 3 improved astrometric precision, extended radial velocity measurements to fainter stars, and added detailed astrophysical parameters such as stellar temperatures, luminosities, and chemical indicators. The combination of these improvements allowed for even more reliable stream identification and characterization. One of Gaia's most transformative contributions is the ability to work in 6-dimensional phase space. For each star, Gaia provides 3 spatial coordinates and up to 3 velocity components. This full phase space information is critical for disentangling overlapping structures in the halo. In position alone, multiple streams can cross the same region of the sky. In velocity alone, different populations can share similar speeds. In full 6-dimensional phase space, however, genuine streams stand out as compact, coherent structures. Their stars cluster tightly in velocity space while remaining elongated in position space, exactly as predicted by tidal disruption theory. This capability allows astronomers to reconstruct orbits directly. By integrating the observed positions and velocities of stream stars through models of the Milky Way's gravitational potential, researchers can infer the past trajectories of their progenitors. This makes it possible to estimate when a stream formed, how many orbits it has completed, and how its progenitor was disrupted. Gaia also enabled the identification of large-scale kinematic structures that were previously hidden. One of the most significant discoveries made using Gaia data is the recognition of major accretion events that shaped the Milky Way's inner halo. These events are not individual streams but broad overlapping populations of stars with common orbital properties. Gaia revealed that a substantial fraction of the halo originated from a small number of massive mergers early in the galaxy's history. For stellar streams specifically, Gaia's data allow detailed measurements of internal velocity dispersions. Thin streams show dispersions well below 1 kilometer per second, consistent with globular cluster origins. Thicker streams display dispersions of several kilometers per second, matching expectations for dwarf galaxy progenitors. These measurements provide quantitative confirmation of theoretical models developed decades earlier. Distance measurements from Gaia parallaxes further strengthen stream identification. Even though parallaxes become less precise at large distances, statistical techniques allow reliable distance estimates for groups of stars. This makes it possible to trace streams in 3 dimensions, revealing their true shapes rather than their projections on the sky. Gaia has also improved the measurement of stream widths and density variations. By mapping stellar positions and motions with uniform precision across the sky, researchers can identify subtle gaps, clumps, and bifurcations within streams. These features carry information about past perturbations, including interactions with dark matter subhalos and the galactic disk. Another important advance is Gaia's ability to connect kinematics with chemistry. While Gaia's onboard spectroscopy provides limited chemical information, its data can be combined with ground-based spectroscopic surveys. By cross-matching Gaia stars with surveys such as Apogee and Lamoste, astronomers can link precise motions with detailed chemical abundances. This combination allows streams to be chemically tagged and their progenitors identified with high confidence. The uniform sky coverage of Gaia is particularly important for halo studies. Earlier surveys were biased toward specific regions of the sky or limited to the galactic plane. Gaia observes nearly the entire sky with consistent sensitivity, enabling a more complete census of halo substructure. This has revealed that the Milky Way's halo is far from smooth, even at large distances. The discovery of dozens of new streams has important implications for understanding the Milky Way's assembly history. Each stream represents a past accretion event, and the number, distribution, and properties of streams constrain models of hierarchical growth. Gaia's results support the view that the Milky Way has experienced a rich merger history, dominated by numerous minor mergers rather than a few major ones. Gaia has also highlighted the limits of detectability. While many streams have been identified, simulations predict that even more should exist, particularly older streams that are more phase-mixed. Gaia's sensitivity sets a practical boundary on how far back in time streams can be traced using kinematics alone. This boundary provides insight into the timescales over which tidal debris remains coherent. From a broader perspective, Gaia has turned the Milky Way into a dynamic laboratory. Instead of inferring galactic evolution from static snapshots, astronomers can now observe motions directly. Stellar streams are among the clearest beneficiaries of this shift, as their defining feature is coherent motion rather than spatial concentration. The Gaia mission continues to operate beyond its original nominal lifetime, and future data releases are expected to further improve precision and extend the reach of its measurements. Each incremental improvement sharpens the view of the halo's substructure and reveals fainter, colder streams. In practical terms, Gaia has moved stellar stream research from the era of individual case studies to a statistical science. Streams can now be catalogued, classified, and compared systematically. Their collective properties can be used to test models of dark matter, galactic potentials, and hierarchical assembly with unprecedented rigor. The Gaia revolution is therefore not defined by a single discovery, but by a transformation in how the Milky Way is studied. By providing full six-dimensional phase space information for vast numbers of stars, Gaia has made it possible to identify, analyze, and interpret stellar streams as fundamental components of galactic structure. With this foundation in place, the focus naturally shifts toward what these streams can reveal beyond their mere existence. Their fine structure encodes information about the invisible mass of the galaxy, including dark matter substructure, and about the detailed shape of the Milky Way's gravitational potential. Understanding these aspects requires using streams not just as remnants of past mergers, but as precision tools for probing the galaxy itself. Around 2018, a major restructuring of the Milky Way's formation history occurred, driven not by a new telescope, but by a new way of seeing stellar motion. Analyses of Gaia's second data release revealed that a large fraction of stars in the inner halo shared a distinctive dynamical signature. These stars moved on highly elongated, almost radial orbits, plunging toward the galactic center and then arcing back out again. Their motions were unlike those of stars formed within a stable disk. The pattern pointed to a single, ancient accretion event of exceptional scale. This event is now known as Gaia Enceladus, also widely referred to as the sausage event due to the elongated shape these stars occupy in velocity space. The identification emerged independently from several research groups in 2018, all using Gaia Doctor 2 astrometry combined with chemical abundance data from large spectroscopic surveys. What they found was not a narrow stellar stream, but a broad population of stars sharing common orbital and chemical properties, indicating a massive merger early in the Milky Way's history. The defining feature of Gaia Enceladus stars is their orbital eccentricity. Unlike disk stars, which move on nearly circular orbits, these stars follow trajectories with eccentricities often exceeding 0.8. In physical terms, this means their orbits are extremely elongated. They pass close to the galactic center at pericenter, then travel far out into the halo before returning inward. The result is a stellar population with large radial motions and relatively little rotational support. When plotted in velocity space, these stars form a distinctive elongated structure, symmetric about zero rotation. This feature was immediately recognizable once Gaia provided precise proper motions across the sky. Prior to Gaia, similar stars had been observed locally, but their global coherence was not apparent. Gaia revealed that they represent a dominant component of the inner stellar halo. Age dating and chemical analysis place the Gaia-Enceladus merger at approximately 8 to 11 billion years ago. This corresponds to a time when the universe was roughly 3 to 5 billion years old. At that epoch, the Milky Way itself was still assembling its disk and had not yet reached its present mass. The merger therefore occurred during a formative stage of galactic evolution, when the structure of the galaxy was particularly sensitive to external perturbations. Chemical abundances provide strong evidence that Gaia Enceladus stars originated in an external galaxy. Compared to stars formed in the Milky Way disk, they exhibit lower ratios of alpha elements to iron at a given metallicity. This pattern reflects slower chemical enrichment, consistent with star formation in a smaller system with a lower star formation rate. These abundant signatures are difficult to reproduce through internal processes alone. The metallicity distribution of Gaia Enceladus stars spans a wide range, from very metal-poor stars to populations approaching 1/3 solar metallicity. This spread indicates an extended star formation history within the progenitor galaxy prior to its merger with the Milky Way. Such chemical diversity is typical of dwarf galaxies rather than globular clusters, confirming the scale of the event. Reconstructing the mass of the Gaia Enceladus progenitor requires combining kinematic, chemical, and dynamical evidence. Estimates suggest that the stellar mass of the accreted galaxy was on the order of several 100 million solar masses. When dark matter is included, the total mass is inferred to have been comparable to that of the Small Magellanic Cloud. This places Gaia Enceladus among the most massive merger events experienced by the Milky Way. Such a merger would have had profound consequences. The accreted galaxy's stars were deposited primarily into the inner halo, where they now dominate the stellar population beyond the thick disk. Today, a significant fraction of halo stars within about 30,000 light-years of the galactic center are thought to originate from this single event. This explains why the inner halo shows relatively coherent kinematic and chemical properties compared to the outer halo, which is built from many smaller accretions. The radial nature of Gaia Enceladus orbits reflects the geometry of the merger. Simulations indicate that the progenitor galaxy fell in on a low angular momentum trajectory, plunging nearly head-on into the Milky Way's potential. As dynamical friction slowed the orbit, repeated passages through the inner galaxy stripped stars and dark matter, depositing debris on radial orbits aligned with the original infall direction. This process contrasts sharply with the formation of thin stellar streams. Gaia Enceladus did not produce a single narrow stream, but rather a broad cloud of debris spread over a large region of phase space. The difference arises from the mass of the progenitor and the timing of the merger. Early, massive mergers experience rapid phase mixing and violent relaxation, which erase thin, stream-like features and produce smoother halo components. The impact of Gaia Enceladus extended beyond the halo. One of the most important consequences was the heating of the Milky Way's disk. At the time of the merger, the disk was already forming, but was thinner and dynamically colder than it is today. The gravitational perturbation from a massive infalling galaxy injected energy into disk stars, increasing their random motions and lifting them to higher altitudes above the galactic plane. This process is widely regarded as a primary contributor to the formation of the Milky Way's thick disk. Thick disk stars exhibit larger vertical scale heights and higher velocity dispersions than thin disk stars, along with older ages and distinct chemical signatures. The timing of thick disk formation aligns closely with the estimated epoch of the Gaia-Enceladus merger, supporting a causal connection. Quantitatively, disk heating from a merger of this scale can increase stellar velocity dispersions by tens of kilometers per second, equivalent to increases of several tens of miles per second in random motion. Such heating is sufficient to transform a thin, cold disk into a thicker, more dynamically excited structure. Subsequent gas accretion and star formation then rebuild a new thin disk within this thickened component. The Gaia Enceladus event therefore represents a transition point in the Milky Way's evolution. Before the merger, the galaxy was a smaller, more fragile system. Afterward, it possessed a massive stellar halo, a heated, thick disk, and a deeper gravitational potential capable of sustaining long-term disk growth. Evidence for this event also appears in the spatial distribution of stars. Gaia Enceladus debris is more concentrated toward the inner regions of the galaxy, unlike many later accretions that populate the outer halo. This concentration reflects the early timing of the merger, when the Milky Way's potential well was shallower and debris could not be deposited at very large radii. The identification of Gaia Enceladus resolved long-standing questions about the origin of the inner halo. Earlier models struggled to explain why inner halo stars exhibited such distinct kinematic properties compared to outer halo populations. Gaia data showed that this distinction arises naturally if the inner halo is dominated by a single major accretion event, while the outer halo is built from numerous smaller ones. This insight also reframed the role of stellar streams in galactic archaeology. Not all accretion events leave behind thin, easily recognizable streams. The most massive and ancient mergers leave broader, more diffuse signatures that require full phase space information to identify. Gaia Enceladus exemplifies this regime, where the evidence lies in velocity distributions rather than spatial filaments. From a cosmological perspective, the Gaia Enceladus merger fits comfortably within the expectations of hierarchical structure formation. Simulations predict that Milky Way mass galaxies should experience one or two significant mergers early in their history, followed by many minor accretions. Gaia Enceladus appears to be the dominant early merger for the Milky Way, shaping much of its present structure. The event also sets constraints on the galaxy's later evolution. A merger of similar magnitude occurring at later times would likely have destroyed the thin disk entirely. The survival and regrowth of the disk imply that no comparable mergers have occurred in the last 8 billion years. This places strong limits on the Milky Way's recent accretion history and explains the relative dynamical calm of the disk today. Gaia Enceladus thus represents a cornerstone in the reconstruction of the Milky Way's past. It connects kinematics, chemistry, and structure into a coherent narrative of early growth through a major merger. It explains the origin of the inner halo, the formation of the thick disk, and the transition from a chaotic early galaxy to the more stable system observed today. As Gaia data continue to improve and are combined with deeper spectroscopic surveys, the details of this event are being refined. The exact orbit, mass evolution, and duration of the merger are subjects of ongoing study. Even so, the broad picture is clear. Gaia Enceladus was a transformative encounter, one that permanently reshaped the Milky Way. Understanding this event provides essential context for interpreting the many thinner streams discovered throughout the halo. Those streams trace later smaller accretions. Gaia Enceladus marks an earlier epoch when the galaxy's structure was still taking shape and when a single merger could redefine its future. Stellar streams move through the Milky Way as extended, coherent test particles. Their defining property is not their brightness or shape, but their sensitivity to gravity. Once stars are stripped from a progenitor system, their subsequent motion is governed almost entirely by the gravitational potential of the host galaxy. This makes stellar streams precise traces of the invisible mass that dominates that potential. Dark matter. In a galaxy like the Milky Way, visible matter accounts for only a minority of the total mass. Stars, gas, and dust dominate the central regions, but beyond the disk, dark matter controls the dynamics. The stellar halo, where most streams are found, is a regime in which dark matter overwhelmingly determines orbital motion. As a result, the geometry, curvature, and internal structure of stellar streams encode information about the galactic gravitational field with high fidelity. The reason streams trace the gravitational potential so accurately lies in their formation mechanism. When stars are stripped from a satellite, they leave with velocities only slightly offset from the progenitor's orbit. Their subsequent trajectories differ mainly in orbital phase rather than in orbital shape. This produces elongated structures that follow the contours of the underlying potential. Any deviation from a smooth, static gravitational field leaves an imprint on the stream's morphology and kinematics. In an idealized galaxy with a perfectly smooth and static potential, a stellar stream would remain a thin, continuous ribbon. Its width and density would evolve predictably as stars gradually separate along the orbit. In reality, the Milky Way's potential is neither perfectly smooth nor static. It contains substructure, evolves over time, and includes contributions from the disk, bulge, and dark matter halo. Streams respond to all of these components. One of the most important insights of the past 2 decades is that stellar streams are sensitive not only to the global shape of the dark matter halo, but also to its small-scale structure. According to the standard cold dark matter model, galactic halos should contain vast numbers of bound subhalos. These subhalos are concentrations of dark matter that failed to form stars or lost them early, rendering them effectively invisible. Simulations predict that a Milky Way mass halo should host thousands of dark matter subhalos with masses ranging from about 1 million to 100 million solar masses. The majority of these objects contain little or no baryonic matter. As a result, they cannot be detected through conventional astronomical observations. Their gravitational influence, however, remains. When a dark matter subhalo passes near or through a stellar stream, it perturbs the orbits of the stars locally. The interaction does not destroy the stream, but it alters its internal structure. Stars near the point of closest approach receive small velocity kicks. Over time, these perturbations grow into observable features. One of the clearest signatures of such interactions is the presence of gaps in stellar streams. A subhalo encounter can remove stars from a narrow region of the stream, creating an underdensity. As the stream continues to orbit the galaxy, this underdensity stretches and evolves, forming a gap whose size and shape depend on the mass, velocity, and impact geometry of the perturber. In addition to gaps, subhalo interactions can produce density fluctuations, spurs, and asymmetries. Spurs are narrow offshoots of stars displaced from the mainstream track. These features arise when stars receive velocity kicks perpendicular to the stream's orbital plane. Over time, they separate from the main body, forming characteristic forked or feathered structures. The expected mass range of subhalos capable of producing detectable perturbations in streams is approximately 10 to the power of 6 to 10 to the power of 8 solar masses. Objects less massive than this produce perturbations too small to be observed with current data. More massive subhalos are rarer and can cause more dramatic distortions, but are statistically less likely to interact with a given stream. This mass range is particularly important because it lies below the threshold for efficient star formation. Subhalos in this regime are expected to be dark. Stellar streams therefore provide a way to detect and characterize dark matter structures that cannot be seen directly. The sensitivity of a stream to subhalo perturbations depends strongly on its internal properties. Thin, dynamically cold streams, such as those formed by globular clusters, are especially valuable. Their low-velocity dispersions, often well below 1 km per second, make them highly responsive to small gravitational disturbances. Even a modest subhalo can leave a measurable imprint. Thicker streams formed by dwarf galaxies are less sensitive on small scales due to their higher internal velocity dispersions. However, their large spatial extent allows them to probe the gravitational potential over a wide range of radii. Together, thin and thick streams provide complementary constraints on dark matter structure. The interpretation of stream perturbations requires careful modelling. Gaps and density variations can also be produced by other mechanisms, including interactions with giant molecular clouds, the galactic disk, or time-dependent changes in the potential. Disentangling these effects demands detailed simulations that account for all relevant components. Despite these challenges, several streams have already shown features consistent with dark matter subhalo interactions. In some cases, the inferred properties of the perturbers align closely with predictions from cold, dark matter simulations. These results support the existence of a rich population of dark substructure in the Milky Way halo. Stellar streams also provide constraints on the global shape of the dark matter halo. The precession of a stream's orbital plane, its curvature across the sky, and its radial distance variations depend on whether the halo is spherical, oblate, prolate, or triaxial. By fitting models to the observed properties of long streams, astronomers can infer the three-dimensional shape of the halo. These measurements have shown that the Milky Way's dark matter halo is not perfectly spherical. Instead, it exhibits mild flattening and may vary in shape with radius. Such findings place important constraints on galaxy formation models and on the nature of dark matter itself. The ability of streams to probe dark matter extends beyond the cold dark matter paradigm. Alternative dark matter models predict different sub-halo populations. Warm dark matter, for example, suppresses the formation of low-mass structures. In warm dark matter scenarios, the number of sub-halos below about 10 to the power of 8 solar masses is dramatically reduced. This difference has direct observational consequences. If dark matter were warm rather than cold, stellar streams would exhibit fewer gaps and perturbations on small scales. By statistically analysing the frequency and properties of stream features, astronomers can test these competing models. Current observations favour cold, dark matter, but the constraints remain incomplete. The sample of well-characterised streams is still limited, and observational biases affect which features can be detected. As more streams are discovered and mapped with higher precision, the statistical power of these tests will increase. Streams also act as indirect dark matter detectors in a broader sense. They respond to the total gravitational field, including contributions from any non-standard dark matter interactions or modifications to gravity. Any deviation from expected stream behavior can signal new physics, provided astrophysical uncertainties are carefully controlled. Unlike laboratory dark matter detectors, stellar streams integrate their signals over billions of years. They record the cumulative effect of countless interactions, making them sensitive to rare or weak phenomena. This long-term integration is both a strength and a challenge, as it requires reconstructing complex dynamical histories. The combination of precise astrometry, spectroscopy, and numerical modelling has transformed stellar streams into quantitative tools for dark matter research. They bridge the gap between cosmological simulations and observations within the Milky Way, linking small-scale structure to large-scale galaxy formation. From a conceptual standpoint, stellar streams represent fossil records of dark matter. They preserve information about the distribution and granularity of the halo at the times and places where they formed and evolved. Unlike stars in the disk, which are constantly reshaped by internal processes, stream stars retain a memory of past gravitational encounters. As observational capabilities improve, streams will allow increasingly stringent tests of dark matter models. Future surveys will detect fainter streams, measure smaller perturbations, and map halo structure with greater resolution. Each new detection adds to a growing archive of dynamical evidence. In this role, stellar streams occupy a unique position in astrophysics. They are both remnants of galactic cannibalism and precision instruments for probing the invisible mass that governs cosmic structure. By studying their fine structure, astronomers gain access to information that cannot be obtained through any other means. The fossil record encoded in stellar streams therefore extends beyond the history of individual galaxies. It reaches into the fundamental nature of dark matter itself, offering one of the most direct astrophysical tests of the physics that shapes the universe on the largest scales. Stellar streams are not unique to the Milky Way. They appear wherever galaxies have grown through accretion, which means they are expected throughout the universe. Observing them beyond our own galaxy provides an external perspective on the same physical processes, free from the limitations imposed by our position inside the Milky Way. These extragalactic streams confirm that tidal disruption and hierarchical growth are universal features of galaxy evolution. The clearest and most extensively studied example outside the Milky Way is found in the Andromeda Galaxy, also known as M31. As the nearest large spiral galaxy to the Milky Way, Andromeda offers a unique opportunity to study halo substructure from the outside, with a nearly face-on view of its extended stellar environment. One of the most prominent features in Andromeda's halo is the giant stellar stream. This structure was discovered in the early 2000s through wide-field photometric surveys that revealed a large overdensity of red giant stars south of Andromeda's disk. Subsequent distance and kinematic measurements confirmed that these stars form a coherent tidal stream associated with a disrupted satellite galaxy. The giant stellar stream of M31 extends for approximately 300,000 light-years in total length. This makes it one of the longest stellar streams known in the local universe. The stream is not a simple arc. It exhibits variations in width, density, and distance along its length, indicating a complex disruption history involving multiple orbital passages. Distance measurements place different segments of the stream at varying depths along the line of sight. Some portions lie tens of thousands of light-years closer to the Milky Way than Andromeda's main disk, while others extend farther behind it. This three-dimensional structure allows astronomers to reconstruct the orbit of the progenitor galaxy and infer the shape of Andromeda's gravitational potential. Kinematic studies show that the stars in the giant stellar stream move on highly eccentric orbits, consistent with a massive progenitor that plunged deep into Andromeda's potential well. Modelling suggests that the original satellite had a stellar mass of several 100 million solar masses, comparable to the more massive dwarf galaxies known in the local group. Most of that mass has now been redistributed into the halo. Chemical abundance measurements reveal a broad metallicity distribution within the stream. This indicates that the progenitor galaxy experienced extended star formation before disruption, similar to the Sagittarius dwarf in the Milky Way. The similarities between these two systems reinforce the idea that large spiral galaxies commonly accrete and dismantle dwarf galaxies of comparable scale. Beyond Andromeda, stellar streams have been detected around many other nearby galaxies, particularly massive spirals and ellipticals. These detections rely heavily on deep imaging with the Hubble Space Telescope and large ground-based telescopes equipped with wide-field cameras. In these systems, streams often appear as faint arcs, shells, or plumes surrounding the main galaxy. Observations of streams in NGC galaxies have revealed a wide diversity of morphologies. Some galaxies display long, narrow streams similar to those seen in the Milky Way. Others show broad shells or umbrella-like structures produced when satellites are disrupted on more radial orbits. These features provide insight into the orbital characteristics of accreted systems and the assembly history of their hosts. A key limitation in extragalactic stream studies is surface brightness. Stellar streams are extremely faint. Typical surface brightness values are around 30 magnitudes per square arc second, sometimes even fainter. At these levels, streams lie at the edge of detectability for most instruments. Small changes in background subtraction, scattered light, or detector sensitivity can determine whether a stream is visible at all. To put this in context, the night sky itself has a surface brightness of roughly 22 magnitudes per square arc second. Stellar streams are therefore about 1,500 times fainter than the sky background. Detecting them requires long exposure times, careful calibration, and meticulous data processing. Distance compounds this challenge. In the Milky Way, individual stream stars can be resolved and studied directly. In Andromeda and more distant galaxies, streams are detected primarily through unresolved stellar light or through counts of specific tracer populations such as red giant branch stars. This limits the available kinematic information and makes it difficult to separate overlapping structures along the line of sight. Crowding is another obstacle. In dense regions near galactic disks, faint streams can be obscured by brighter stellar populations. Dust extinction, background galaxies, and foreground stars further complicate the analysis. As a result, most detected extragalactic streams are found in the outer halos of galaxies, where background contamination is lower. Despite these challenges, systematic surveys have shown that streams are common. Deep imaging campaigns targeting nearby galaxies frequently reveal halo substructure once sufficient depth is reached. This suggests that the apparent smoothness of many galactic halos in shallower images is an observational artifact rather than a true physical property. The inability to resolve individual stars in most extragalactic streams also limits chemical analysis. Unlike Milky Way streams, where detailed abundance patterns can be measured, extragalactic streams are studied primarily through integrated light or color magnitude distributions. These methods provide coarse metallicity estimates, but cannot yet match the precision achieved within our own galaxy. Nevertheless, extragalactic streams offer important advantages. Observing a galaxy from the outside allows the full spatial extent of streams to be mapped without projection effects caused by our internal vantage point. This makes it easier to identify global patterns such as symmetry, wrapping, and alignment with the host galaxy's halo. Extragalactic streams also provide statistical context. By comparing stream populations across many galaxies, astronomers can test whether the Milky Way's merger history is typical or unusual. Current evidence suggests that large spiral galaxies commonly host multiple streams, indicating that the Milky Way is not exceptional in this regard. The study of streams beyond the Milky Way also informs models of dark matter. Just as in our galaxy, the shapes and orientations of extragalactic streams reflect the gravitational potentials of their hosts. Although the data are less detailed, broad constraints on halo shape and mass distribution can still be derived. Future instruments will significantly improve this field. Next-generation surveys will reach lower surface brightness limits over wider areas, increasing the number of detectable streams. Improved resolution and sensitivity will allow fainter and more distant features to be identified, extending stream studies beyond the local group. As observational limits continue to be pushed, stellar streams are emerging as a universal feature of massive galaxies. They provide direct evidence that accretion and tidal disruption are ongoing processes across cosmic time. The giant stellar stream of Andromeda stands as a nearby, large-scale example, while more distant streams demonstrate that similar events have shaped galaxies throughout the universe. By placing the Milky Way in this broader context, extragalactic streams confirm that our galaxy's history of accretion and disruption is part of a general pattern. The same physical laws operate everywhere. Galaxies grow by consuming smaller systems, and the remnants of those events persist as faint, extended structures that trace gravity on the largest scales. Chemical abundances provide one of the most powerful tools for reconstructing the formation history of the galaxy. While stellar motions reveal how stars move through the gravitational potential, their chemical compositions record where and how they formed. In the context of stellar streams, chemistry turns kinematic structures into historical records, allowing astronomers to identify common origins, trace star formation histories, and separate stars formed inside the galaxy from those accreted from external systems. Every star forms from a specific mixture of elements present in the gas at the time and place of its birth. These elements are produced by earlier generations of stars through nuclear fusion and supernova explosions. Once a star forms, its overall chemical composition remains largely unchanged for the rest of its life. This makes stars long-lived chemical traces of their birth environments. Elemental abundance tagging relies on this principle. By measuring the relative abundances of key elements such as iron, Fe, magnesium, Mg, calcium, Ca, and barium, Ba, astronomers can group stars that form together, even if they are now widely separated in space. These elements are chosen because they are produced by different nucleosynthetic processes and on different timescales, providing complementary information. Iron, Fe, is primarily produced in Type Ia supernovae, which originate from white dwarf systems and occur on timescales of roughly 1 billion years after star formation. Magnesium, Mg, and calcium, Ca, are alpha elements produced mainly in core collapse supernovae from massive stars, which explode within tens of millions of years. Barium, Ba, is produced largely through slow neutron capture processes in asymptotic giant branch stars, which enrich the interstellar medium on intermediate timescales. The relative ratios of these elements encode the duration and intensity of star formation in a system. A high ratio of alpha elements to iron indicates rapid star formation dominated by massive stars. Lower alpha to iron ratios signal prolonged star formation, allowing time for Type Ia supernovae to contribute iron. Barium abundances provide additional constraints on intermediate mass stellar populations and enrichment timescales. Stellar streams preserve these chemical signatures. Stars in a given stream typically share similar abundance patterns, reflecting their origin in a single progenitor system. In globular cluster streams, this chemical uniformity is extreme. Iron abundances often vary by less than a few hundredths of a dex, confirming that these stars formed from a well-mixed gas reservoir in a short burst. Streams originating from dwarf galaxies display a very different chemical structure. Dwarf galaxies form stars over extended periods and in less efficient environments. Their chemical enrichment proceeds slowly, leading to broad metallicity distributions and distinctive abundance patterns. When such a galaxy is disrupted, its stream inherits this chemical diversity. Metallicity gradients along streams provide particularly valuable information. Observations show that in many dwarf galaxy streams, stars closer to the surviving remnant are more metal-rich, while stars farther along the stream are more metal-poor. This gradient arises naturally from the internal structure of the progenitor. More metal-rich stars tend to form later and are more centrally concentrated, while older metal-poor stars populate the outskirts and are stripped first. By measuring how metallicity changes with position along a stream, astronomers can reconstruct the internal chemical structure of the progenitor galaxy before disruption. This allows constraints to be placed on the galaxy's mass, star formation efficiency, and gas retention history. Such reconstructions are otherwise impossible once the progenitor has been fully dissolved. Chemical abundances also reveal the star formation histories of stream progenitors. The presence of stars with a wide range of metallicities indicates prolonged star formation lasting several billion years. Narrow metallicity distributions imply short-lived star formation episodes. Abundance ratios further refine this picture by constraining the relative contributions of different supernova types over time. These chemical signatures are essential for distinguishing between stars formed inside the main galaxy and those accreted from external systems. In the Milky Way, stars formed in the disk exhibit characteristic abundance patterns shaped by high star formation efficiency and sustained gas inflow. At a given metallicity, disk stars tend to show higher alpha element abundances than stars formed in dwarf galaxies. Accreted stars, by contrast, often show lower alpha to iron ratios at the same metallicity. This reflects slower chemical evolution in their progenitor systems. By combining chemical information with kinematics, astronomers can classify stars as in situ or accreted with high confidence. Stars on halo-like orbits with dwarf galaxy-like chemical patterns are strong candidates for accreted origin. Stellar streams provide clean laboratories for this classification. Because stream stars share a common origin, their chemical patterns can be studied without contamination from unrelated populations. This reduces ambiguities that arise when analysing individual field stars whose origins are uncertain. In some cases, chemical tagging has revealed that multiple streams originate from distinct progenitors even when they overlap spatially. Streams that cross the same region of the sky can be disentangled based on differences in metallicity and abundance ratios. This demonstrates the power of chemistry to separate structures that would otherwise be confused. The concept of streams as time capsules follows directly from these properties. Each stream preserves the chemical state of its progenitor galaxy at the time stars were stripped. Because stripping occurs over multiple orbits, a single stream can contain stars removed at different epochs. These stars record the chemical sequence of the progenitor's evolution over time. Older, more metal-poor stars in a stream reflect early star formation when the progenitor's gas was relatively unenriched. Younger, more metal-rich stars indicate later periods of star formation before disruption. By dating these populations using stellar ages and abundance patterns, astronomers can reconstruct a timeline of star formation extending back to the early universe. This approach provides insight into conditions at epochs that are otherwise inaccessible. Many dwarf galaxies that contributed stars to the halo no longer exist as bound systems. Their streams are the only surviving evidence of their internal structure and chemical evolution. Without streams, this information would be permanently lost. Chemical analysis of streams also informs models of galaxy formation. The relative contributions of different progenitor types, inferred from abundance patterns, constrain how much of the halo formed through massive mergers versus numerous small accretions. The chemical diversity of the halo reflects the diversity of its building blocks. Recent large spectroscopic surveys have greatly expanded the reach of this work. By combining precise astrometry with detailed abundance measurements, astronomers can map chemical signatures across entire streams. This has transformed galactic archaeology from a qualitative exercise into a quantitative science. The results consistently show that the Milky Way's halo is chemically composite. Some components originate from massive chemically evolved progenitors. Others come from small, metal-poor systems that formed stars, briefly and inefficiently. Streams preserve these distinctions clearly. In this sense, stellar streams function as archival records of early star formation. They retain information about the timing, duration, and efficiency of star formation in galaxies that no longer exist. Each stream represents a chapter in the galaxy's assembly history, written in elemental abundances rather than words. By reading these chemical records alongside kinematic data, astronomers can reconstruct not only how stars move today, but how entire galaxies formed and evolved billions of years ago. Streams, therefore, bridge stellar astrophysics and cosmology, connecting nuclear processes inside stars to the large-scale growth of galaxies. Through their chemical fingerprints, stellar streams preserve the memory of environments long gone. They are not merely debris scattered through the halo. They are durable records of early star formation, offering a direct link between present-day observations and the formative stages of galaxies in the young universe. The study of stellar streams is entering a new observational era. While Gaia transformed our ability to measure stellar motions within the Milky Way, it does not operate in isolation. A new generation of wide-field imaging surveys and space-based observatories is poised to extend stream science deeper, fainter, and farther than before. Together, these facilities will dramatically expand the sensors of stellar streams, refine models of the galaxy's mass distribution, and allow the Milky Way's merger history to be reconstructed with unprecedented resolution. A central role in this next phase will be played by the Vera C. Rubin Observatory, located on Cerro Pachon in Chile. The Rubin Observatory is designed to carry out the legacy survey of space and time, commonly referred to as LSST. Full science operations are expected to begin in the mid-2020s following commissioning and early survey phases. The LSST will repeatedly image the entire southern sky over a 10-year period, producing a deep, time-resolved map of billions of stars and galaxies. Each region of the sky will be observed hundreds of times, allowing faint structures to be detected through image stacking and careful background subtraction. For stellar stream studies, depth and uniformity are the key advances. The Rubin Observatory will reach surface brightness limits significantly fainter than most existing wide-field surveys. While Gaia excels at astrometry, it becomes incomplete at faint magnitudes and large distances. The LSST will complement Gaia by detecting vast numbers of faint halo stars that Gaia cannot measure precisely. This includes main sequence turn-off stars and lower mass stars at distances well beyond 100,000 light-years. These capabilities are critical for stream discovery. Many stellar streams are expected to exist at extremely low surface brightness, approaching or exceeding 30 magnitudes per square arc-second. Such structures are invisible in shallower surveys, but become detectable when deep, homogeneous imaging is available across large areas of sky. Simulations of Milky Way-like halos predict the presence of hundreds of stellar streams, most of them originating from low-mass globular clusters or ancient dwarf galaxies that were disrupted long ago. Only a fraction of these streams are currently known. The LSST is expected to reveal many of the missing ones, particularly older and more diffuse streams that are difficult to identify kinematically. The Rubin Observatory will also enable precise photometric selection of stream member stars. By mapping color magnitude diagrams across the halo, astronomers can isolate stellar populations with similar ages and metallicities. When combined with Gaia proper motions for brighter stars, this will allow streams to be traced continuously from the inner halo to its outermost regions. Time domain data add another dimension. Variable stars, such as RR Lyrae, serve as precise distance indicators and are abundant in old, metal-poor populations typical of stellar streams. The LSST will identify large numbers of these variables, allowing three-dimensional mapping of streams across the halo with improved distance accuracy. While Rubin provides depth and coverage, space-based observations will add precision and stability. The Nancy Grace Roman Space Telescope, scheduled for launch later in the 2020s, will play a complementary role. Roman is designed for wide-field imaging and spectroscopy in the near-infrared, with sensitivity and resolution exceeding that of previous space telescopes over large areas of sky. Roman's wide-field instrument will be particularly valuable for mapping the stellar halo in regions affected by dust extinction, such as near the galactic plane. Infrared observations penetrate dust more effectively than optical surveys, revealing populations that are difficult to study from the ground. This will help complete the census of streams whose orbits carry them through obscured regions. The Roman Space Telescope will also provide high-quality photometry and, for selected targets, spectroscopy. These data will improve estimates of stellar ages, metallicities, and distances for stream stars. When combined with Gaia astrometry, Roman observations will enhance six-dimensional phase space reconstruction for faint and distant streams. One of the most significant outcomes of these combined surveys will be the discovery of hundreds of additional stellar streams. This expansion is not merely a matter of quantity. A larger sample enables statistical studies that are currently impossible. Instead of analysing streams individually, astronomers will be able to examine the distribution of stream properties across the halo. Such studies will address questions about the typical masses of progenitor systems, the timing of accretion events, and the spatial distribution of debris. They will also clarify how stream properties vary with galactocentric distance, orbital inclination, and progenitor type. These patterns encode the assembly history of the galaxy in aggregate. An expanded stream catalogue will also sharpen models of the Milky Way's gravitational potential. Stellar streams act as extended probes of the mass distribution, sampling the potential along their entire orbits. With many streams at different orientations and radii, it becomes possible to constrain the shape and radial profile of the dark matter halo with much higher precision. Improved mass models will address long-standing uncertainties. Current estimates of the Milky Way's total mass vary by nearly a factor of 2, largely due to limited constraints at large radii. Streams extending beyond 100,000 light-years provide direct information about the gravitational field in these regions. As more such streams are mapped, mass estimates will converge. The shape of the halo is another key parameter. Whether the halo is spherical, oblate, prolate, or triaxial has implications for dark matter physics and galaxy formation. Different stream orbits respond differently to halo shape, causing variations in precession and alignment. A large ensemble of streams will allow these effects to be disentangled robustly. Time-dependent aspects of the potential can also be probed. The Milky Way has grown over time, and its disk has evolved. These changes leave subtle imprints on stream morphology. By modelling streams of different ages, astronomers can infer how the galaxy's mass distribution has changed over billions of years. Beyond global properties, future surveys will improve sensitivity to small-scale perturbations. With more thin streams mapped at higher resolution, the frequency and characteristics of gaps and density fluctuations can be measured statistically. This will strengthen constraints on the population of dark matter subhalos and test predictions of cold versus warm dark matter models. The increased data volume also enables more detailed reconstruction of the Milky Way's merger history. Each stream corresponds to a specific accretion event. By estimating the ages of streams and their progenitor masses, astronomers can build a timeline of mergers extending back to the earliest epochs of galaxy formation. This reconstruction goes beyond identifying major events like Gaia and Enceladus. It includes the accumulation of many smaller accretions that collectively built the halo. The relative importance of early massive mergers versus late minor accretions can be quantified, providing a direct test of hierarchical structure formation models. Chemical information will play a central role in this effort. Combining deep imaging with spectroscopic follow-up from ground-based facilities will allow streams to be chemically tagged and linked to progenitor types. This adds an independent dimension to merger reconstruction, connecting dynamical events with star formation histories. The integration of these datasets requires advanced modelling techniques. Numerical simulations of galaxy formation and tidal disruption will be increasingly constrained by observations. Streams will serve as benchmarks against which models of the Milky Way must be tested, forcing improvements in both baryonic and dark matter physics. From a broader perspective, the Milky Way will become one of the best understood galaxies in the universe. While distant galaxies provide statistical samples, only in our own galaxy can individual stars be resolved and tracked in detail. The next generation of surveys will exploit this advantage fully. The result will be a shift from a qualitative narrative of galactic growth to a quantitative reconstruction. Instead of stating that the Milky Way formed through mergers, astronomers will be able to specify when those mergers occurred, how massive the progenitors were, and how their debris is distributed today. This level of detail has implications beyond galactic astronomy. It provides boundary conditions for cosmological simulations and tests fundamental assumptions about dark matter and structure formation. The Milky Way becomes not just a case study, but a reference system for understanding galaxy evolution more generally. As the Rubin Observatory and the Roman Space Telescope begin delivering data, stellar stream research will move into a phase of rapid expansion. New discoveries will be routine rather than exceptional. The challenge will shift from finding streams to interpreting them within a coherent theoretical framework. In this next wave, stellar streams are no longer isolated curiosities. They become a comprehensive mapping tool linking the present-day structure of the Milky Way to its full assembly history. Each newly identified stream adds resolution to that map, refining our understanding of how a large, spiral galaxy was built, piece by piece, over cosmic time. Stellar streams are long-lived structures, but they are not permanent. Their existence reflects a balance between coherence and dispersion governed by galactic dynamics. Over time, the same gravitational processes that create streams also work to erase them. Understanding the long-term fate of stellar streams requires examining phase mixing, orbital evolution, and the continued growth of the Milky Way itself. Once stars are stripped from a progenitor system, they occupy a narrow region of phase space. They share similar orbital energies and angular momenta, which allows them to remain dynamically coherent over long periods. This coherence is the defining feature that allows streams to be identified. However, even small differences in orbital parameters lead to gradual divergence. This process is known as phase mixing. Phase mixing occurs because stars with slightly different orbital periods slowly drift apart in orbital phase. Over successive orbits around the galaxy, these small differences accumulate. Stars that were once close together along the stream spread out, filling a larger fraction of the orbit. The stream becomes longer, broader and lower in surface density. Importantly, this process does not require external perturbations. It arises naturally from the internal dynamics of the system. The rate of phase mixing depends strongly on orbital properties. Streams on short-period orbits in the inner galaxy experience rapid mixing. Their orbital periods are typically a few 100 million years, and the gravitational potential varies strongly with position. As a result, phase mixing proceeds efficiently, and the stream's contrast against the background halo diminishes relatively quickly. In the outer halo, conditions are different. Orbital periods can reach several billion years, and the gravitational potential changes more slowly with radius. Streams in these regions phase mix much more slowly. This allows them to remain identifiable for extended periods, even if they formed early in the galaxy's history. Numerical simulations and analytical models indicate that stellar streams can remain detectable for approximately 5 to 10 billion years, depending on their location and progenitor type. Thin streams from globular clusters with very low internal velocity dispersions often persist longer as coherent structures. Thicker streams from dwarf galaxies disperse more rapidly in phase space, but their higher stellar content can keep them observable for comparable timescales. As phase mixing progresses, streams transition from narrow filaments into broader, more diffuse components of the stellar halo. Their spatial overdensity weakens, and their kinematic signature becomes harder to isolate. Eventually, the stream's stars become indistinguishable from the smooth halo population using position alone. At that stage, identification requires precise kinematics or chemical information, and even these signatures weaken over time. When the memory of a merger fades, it does not vanish entirely. Instead, it becomes encoded in the global properties of the halo. The smooth stellar halo represents the cumulative result of many past accretion events whose individual signatures have been erased by phase mixing. The halo's density profile, velocity dispersion, and chemical distribution all retain information about this integrated history. In this sense, stellar streams occupy an intermediate stage between bound satellites and the fully mixed halo. They are visible reminders of recent or moderately ancient mergers. Older mergers contribute to the background halo without leaving distinct streams. The absence of a stream does not imply the absence of accretion. It indicates that sufficient time has passed for dynamical processes to erase coherent structure. The continued evolution of streams is also influenced by external perturbations. Interactions with the galactic disk, giant molecular clouds, and dark matter subhalos introduce additional sources of orbital diffusion. These interactions accelerate the broadening of streams and the loss of coherence. In the inner galaxy, repeated disk crossings are particularly effective at heating streams and promoting dissolution. The Milky Way's gravitational potential itself evolves over time. As the galaxy accretes mass and its disk grows, the potential deepens and changes shape. Streams respond to these changes through orbital precession and deformation. time-dependent effects further complicate the interpretation of old streams and contribute to their gradual erasure. Despite these processes, the Milky Way does not represent a closed system. Accretion has not ended. Several satellite galaxies continue to orbit the Milky Way today, and tidal stripping is actively occurring. New streams are forming even as older ones dissolve. The future accretion history of the Milky Way is expected to be dominated by minor mergers. Cosmological models predict that no mergers comparable in scale to Gaia and Enceladus are likely to occur in the next several billion years. Such an event would significantly disrupt the galactic disk, which appears dynamically stable and long-lived. Instead, the galaxy will continue to accrete low-mass dwarf galaxies and globular clusters. Each of these systems will contribute stars to the halo through tidal stripping. New streams will form, adding fresh structure to the halo even as older streams fade. This continuous cycle maintains a dynamic equilibrium between the creation and destruction of substructure. One notable future interaction involves the Large Magellanic Cloud, whose mass and proximity make it a significant perturber of the Milky Way's halo. Its eventual merger, several billion years in the future, will deposit substantial material into the halo and likely generate new streams and shells. This event will leave a long-lasting imprint on the galaxy's structure. Over cosmic time, the balance shifts. As the rate of accretion declines and existing streams phase mix, the halo becomes smoother. The distinct scars of individual mergers blur together. The galaxy's growth history becomes harder to reconstruct from dynamical substructure alone, requiring increasingly indirect methods. This progression highlights the transient nature of stellar streams. They are not permanent records, but temporary features that persist for a finite interval. Their visibility depends on timing, location, and observational capability. At any given moment, the streams we observe represent a snapshot of recent and intermediate age accretion events rather than the full history of the galaxy. From a broader perspective, this transience is a strength rather than a limitation. Streams provide time-resolved information. Their presence indicates when accretion occurred and where its effects remain dynamically coherent. By combining streams of different ages, astronomers can reconstruct a sequence of events spanning much of the galaxy's lifetime. As streams dissolve, their stars become part of the smooth halo, contributing to its mass and chemical diversity. The halo therefore represents the long-term memory of galactic assembly, while streams represent its short and medium-term memory. Both are necessary for a complete understanding of galaxy formation. In the far future, as the Milky Way continues to evolve and accrete mass, the current population of streams will largely disappear as identifiable structures. New streams will replace them, tracing newer events. The overall halo will grow more massive and more mixed, gradually approaching a state where individual accretion events are no longer dynamically separable. This outcome reflects a general principle of gravitational systems. Order emerges during disruption, then fades through mixing. Stellar streams are manifestations of this process. They form as coherent structures when stars are stripped, then slowly dissolve as gravity redistributes them. In this context, stellar streams can be understood as temporary scars in cosmic time. They mark where and when the galaxy interacted with its surroundings. They persist long enough to be studied in detail, but not long enough to survive indefinitely. Their eventual disappearance is a natural consequence of the same physical laws that created them. By studying streams at different stages of this life cycle, astronomers capture a dynamic view of galactic evolution. The Milky Way is not frozen in its current state. It is continuously shaped by gravity, accretion, and mixing. Stellar streams provide direct evidence of this ongoing process, linking the present structure of the galaxy to both its past interactions and its future evolution. As the record of individual mergers fades, the broader patterns remain. The halo's structure, mass, and composition preserve the integrated outcome of billions of years of growth. Stellar streams, visible for only a fraction of that time, offer a rare opportunity to observe galactic assembly in action before its traces are smoothed away by the long, slow processes of dynamical evolution.